Hey everyone, Mr. Armitage here, coming at you with my sick voice today for the Check Your Understanding that we did today in class on the paper you were given on Friday, the 5th of April. Okay, so here is the Check Your Understanding, right? The original paper is about testing Flint's water. So here, significance test for proportion or step. So sometimes parents and grandparents like to recount how difficult life was when they were kids, such as having to walk 10 plus miles to school in snow uphill both ways. A random sample of 180 teenagers. Okay, so let's make a note of that. That's going to be our sample to keep track of. Random sample of 180 teenagers were selected, and 40% had heard stories from their parents or grandparents. Okay, so that 40%, okay, is tied to the sample, which means that it is the statistic of this problem. Let's see here. Do these data provide convincing evidence at the alpha equals 0.05? Okay, so that's good to know. That's our significance level. Oh, hey, we can just write that right here already. 0.05, because that's what we're comparing it to. The proportion of all teenagers who have heard stories from their parents or grandparents. Okay, so the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids differs from zero point 0.5. Okay, so kind of two things here, right? This tells us how to define the parameter. What color? Okay, so the parameter is the proportion of all teenagers, right? Teenagers who have heard stories. Okay, and I'm just going to cut it off there because I don't need to write the entire thing. We know what it is. There we go. Okay. Now the statistic comes from our sample. Okay. The 180 is the sample size. Okay. I don't know why I wrote 108. 180 is the sample size, while p hat, okay, is the 0.4. Now, if we wanted to, we could say that point or 72 out of 180 is equal to 0.4, but that's not necessary here. Okay, we're fine with this. Okay. We do have an interesting thing happen when we get to our hypotheses, specifically the alternative. Okay, the null hypothesis is always our parameter is equal to something. Here, our proportion is equal to 0.5 right there. Okay, not 0.4. That's for the samples. That's for the statistic. Okay, our 0.5 is there. Okay, now here's the issue with the alternative. Okay, in class, I told you that this was absolutely fine because we already know that p hat was less than 0.5. And in reality, that's what you would do like 99% of the time. Okay. 1% of the time, because you're supposed to write the hypotheses before you ever collect data. Notice how it says differs from. Okay. So it could be less than, or it could be greater than. Okay. So strictly speaking, we should say P is not equal to 0.5. Okay? And there's a really easy way to deal with this situation. All we have to do is double our p-value, okay, which we'll get in a second. Okay, so I'm just going to leave that in orange there, kind of in parentheses, just to remind us. Okay, name of procedure, right? We're still doing a 1 proportion z-test. Okay, so now we need to check the conditions. Okay, and we have our 3 conditions, right? Random. Okay, that's a yes, right? It says random sample, so it's random. Okay, 10% condition. Okay. Is 180 less than or equal to, or at most, 10% of all teenagers? Okay. Now notice, we don't say all teenagers who have heard a story or anything like that. It's all teenagers. It's the group that we took our sample from. Okay. And we said here, a random sample of 180 teenagers. That was their only qualification to be in the group in our sample, that they were teenagers. So there we go. Now, you probably don't know how many teenagers there are. I'm going to assume that this is for the United States, but there are a lot. It's in the millions. So yeah, 180 is fine. Okay. Now we want to deal with the large counts. Right, so our sample size times p. Okay. Our expected number of successes should be at least 10, and the expected number of failures should be at least 10. Okay. Now these work out to the same thing because 0.5 is exactly in the middle. So half of 180 is 90. 90 is bigger than 10. We're good there. Okay, good. So we've met the criteria to actually run our test. So let's go ahead and do it. General formula. Remember, the test statistic is equal to the statistic, sorry, ran out of space, minus the parameter divided by the standard deviation of the sampling distribution. So that means our specific formula here is going to be z equal to p hat minus p divided by the square root of p times 1 minus p over n. Okay. Notice everything on the bottom is inside of the square root. That is an important thing to note. Okay, as far as work goes, right, we're just going to plug stuff in. 0.4 minus 0.5 divided by square root of 0.5 times 1 minus 0.5 divided by 180. Okay. Our negative 0.1 divided by, see, I actually need to calculate this. Oh, wait, I already have it here, actually. 0.037. Okay. That's totally fine for not only this to be negative, right, because we're talking about a value less than 50%, but also it's fine for our test statistic to be negative. And we get about negative 2.70. Okay. It's a 2 after that, so we don't need to worry. Now, as for the p-value, Okay, this is the only time where the different hypotheses, the alternative hypotheses, come into play. Okay, so I'm going to draw a picture and I'm going to use two different colors to kind of show what's happening. Okay, so in the middle here is 0.5, and over here is 0.4. Okay, so our p-value, right now we say p is less than 0.5. We are also less than 0.5, so we want to find this direction here. Now, if we were going to go with the not equals part, okay, we would also have this portion here where this is 0.6 and above, right? Because we might be below the mean, we might be above the mean. Now, it doesn't really make sense for us to do this because we know that our sample is less than 0.5, so that's the direction we should go. But sometimes you have no idea about how it'll go. Right? It might be greater than, might be less than. So the only thing we can test for is that, is it different? So this is what we have. Now, we don't have to calculate the p-value twice. Okay, we don't have to do two separate things and add them together. We can simply take what we get for this p-value here, for the less than 0.5 alternative, and just double it, because the normal distribution is symmetric. So get our normal CDF. Let's see, lower, upper, mean. Okay, that is 0.5, and standard deviation is 0.037. Okay, so as we can see here, our upper is 0.4. It's not the color I wanted to use. 0.4. So our lower is that. That will give us a p-value of the blue alternative that the proportion is less than 0.5. Let's see, 0.037. Go 0.004. Okay. Now, if we were to simply double that, okay, that would be the p-value for the orange alternative hypothesis, that p is not equal to 0.5, simply not equal, 0.0068. Okay. Now notice in this particular case, it did not actually change our conclusion at all. In some situations, it might. So our conclusion, right, we could interpret the p-value, or we could simply do the test conclusion. Now, I don't, some space here, and I don't want this video to go on too long, so I'm just going to say what the result is, say the conclusion. So assuming the null hypothesis is true, p is equal to 0.5, there is a 0.0034 probability of getting a sample proportion of 0.4 or less. Okay. I'm just going to do it for the blue situation. If you wanted to do it for the orange, you can figure that one out. Okay, and then the actual conclusion part after that interpretation, okay, because 0.0034 is less than 0.05, we reject the null. So we do have convincing evidence that the proportion of teenagers who have heard stories from their parents and grandparents is less than 0.5. Now, the second question here, okay, 95% confidence interval for the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids is, okay, 0.328 to 0.472. Explain how the confidence interval is consistent with but gives more information than the test. Okay, now here, if you notice, right, our interval does not contain 0.5, which was the hypothesized amount, the null hypothesis, 0.5. So it's outside of the confidence interval, which means that we would not regard it as a plausible value. So that's how it is consistent. The way it gives us more information is that it gives us actual plausible values, right? 95% confident that the actual proportion of teenagers who have heard stories is between 32.8% and 47.2%. So it gives us a little more information because it gives us the plausible values, but it's consistent still because 0.5 is still not in confidence interval. Okay, hope my voice wasn't too bad, and I know this is running on close to 17 minutes. See you tomorrow.